Hello, everyone. Welcome. I'm Katharyn White, and I lead public sector marketing for Google. And I am your moderator for today. So I'm super excited to be joined by Dr. Nadeem Zafar, who's the director of pathology and laboratory medicine service at the VA, and Scott Frohman, who's a colleague of mine at Google, who heads our defense programs. So what could we possibly have in common, and why are we all here today? Well, the first clue is actually in the introduction here. ARM, the Augmented Reality Microscope, is actually the star of the show, believe it or not. So let's get into some details about why.
Sure.
So maybe to start, let's do some introductions and have some fun. First, Nadeem, maybe you could do a more formal introduction, and then we'll have the fun.
Yeah, my name is Nadeem Zafar. I'm the Chief of Pathology, Director of Pathology at VA Puget Sound in Seattle. Pathologist is considered a physician or a trainer of physicians, and we are the diagnosticians. We are the ones typically making diagnosis of cancer. And we want to make sure that we are absolutely accurate, we don't make mistakes. And this is where this technology is going to come into, and that's going to be, we'll be talking a little bit more about that later.
Super. Scott?
I'm Scott Frohman, and I just started with Google a little over 14 years ago. And I bring all of the innovation that happens in the areas of AI, infrastructure, networking, all kinds of good stuff to the Department of Defense.
So I can tell you this next part of the panel is really worrying to my panelists because they don't know what I'm going to ask, right? So this is a bit of this or that. So all you have to do is tell me your preference. You can tell me why if you want, or you can tell the audience why, just so you know a bit more about them. Okay, sunset or sunrise or sunset? Scott?
Sunrise, morning person.
For me, sunrise as well.
To sunrise. Listening or talking?
Listening.
That's a difficult question.
And there's the answer.
I'm the teacher, so I have to talking, but listening too.
Okay, you can see how exciting this is going to be, right? Vegas or Monte Carlo?
Vegas.
I haven't been to Monte Carlo, but probably Monte Carlo.
That's... Okay, now Nadeem did a bit of this in the intro. Speed or accuracy?
Or accuracy.
Accuracy. See, you got that, you got that.
Nice.
Did that.
Okay, AI or security?
Both.
That's the right answer, AI.
I mean, fortunately with Google you don't have to choose, but Scott already gave you a choice here, so we'll dive into that here. But first, before we dive into what this technology is, what the solution is, what's the problem that we're solving? Nadeem, maybe start with you.
So the problem is my job and the job of so many pathologists who serve you all and your families and your friends is to make sure that what we do is very accurate, that we can identify the disease. We don't overcall something, we don't make a mistake. We want to make sure that the treatment that follows accurately represents our diagnosis. So this is where the technology comes in, and this is why we are so excited about it.
Specifically a cancer diagnosis.
And that's
right?
correct, absolutely. At this point, a cancer diagnosis.
And why, Scott, does Google care about this?
Well, so as I said, I've been with Google for a long time, and we do a lot of really cool things. Google thinks about solving problems in large ways, large movements. You've probably heard 10x many, many times just in the last day and a half here in Vegas. That's what we talk about, quantum movement. And so we don't just want to incrementally improve things like cancer diagnosis. We want to do it at scale. And the nice thing, the other thing I love about being here is we care about our shareholders and stock price, but we care about humanity and good for the world. And this project enables us to think 10x and do something good for humanity.
Now it's powerful, and I can tell you from being at Google just since June, this is quite real for us. So the opportunity to have this intersection of impact on something that matters is quite present in the culture, if I can say. But I think, Nadeem, there's more to this too, problematically. In other words, aren't there limited skills to be able to do the diagnosis, and doesn't time really matter in terms of problem solving?
No, it does. I mean, the technology and the need for it is multi-directional, essentially. At this point in time, we are right at the beginning of where the things are going to go, essentially. And I'll give you an example that this kept coming back to me is, one small step for man and one giant step for mankind. This is how I look at this technology. And this is we're so fortunate to be at that beginning step. So what this does is, this is an opportunity. At this point, it told us, yes, this is a technology that can come in very handy to diagnose cancer, albeit on a small scale at this point in time, albeit in a few conditions. But this has the potential to grow substantially. It can bring consistency across the enterprise, across the diagnostic world, essentially. It can help us train better pathologists. It can help us educate better medical students. It can be used as research and all. And we will talk a little bit more about that.
Okay, so if we sort of summarize the problem, we can say that diagnosing cancer relies on pathologists, very trained, very skilled, very limited resource, who examine these tissue samples under a microscope, which is both time-consuming, I would imagine.
That's correct. Absolutely.
Error-prone.
It is error-prone, and because there's so much variation in disease. I mean, human disease has got a lot of variation. But at this point in time, this is, as we built up this technology, as we train this arm, essentially, it'll be able to recognize more and more diseases. It'll make our job easier. It will enable us to do this job quicker while being more accurate. So we'll be able to handle, and we are not preparing enough pathologists. We are not training enough pathologists, and this is something, there's kind of, there's a quality issue across the world in particular. Even across the US, we make medical errors, essentially. And this technology will help bring those errors down, make us more efficient also.
Okay, so very clear the problem statement. So what did we do to solve it?
That actually,
Go ahead, Scott.
if I could. So I put a slide in here. Could we go to the next slide? So this is a digitized version of a tissue slide. So we basically took a thin slice of a specimen and ran it through a very funky scanner, right? Not the kind that you would make photocopies in the office. And this is the output. And there's some annotations on here. But this slide right here is 14 billion pixels. The size of a tumor on this slide is 400,000 pixels. Now that sounds like a lot of pixels, right, when you think about the pictures that you take. But if you do the math, that is 0.003% of the slide. So when the pathologist is looking, and this is just one slide, right, as I learned from Dr. Zafar, there are often dozens, if not 100 slides to try to identify something in a person. That's a lot of looking, and that's where this error proneness, I think, that you described comes from. So in this slide, you see a zoom in. So the box on the far right up there, that little box in the upper right-hand corner, if you zoom into that, you get this next box below it. And then take that little box inside the box and zoom into that, and this is what you get. Well, that's the size of a tumor. So now think about the size of that down in that first box way up there compared to this entire tissue specimen. And then multiply that by 100 slides that a pathologist
Yeah, so there are two things. I mean, you can have a very, very small sample, and this is all being done. Typically now, this is a digitized image, but the arm is looking at it under a microscope. The challenge for us is to identify where the tumor is, and also if this is distant from where the original tumor is, that means the tumor is beginning to go in other body parts. And sometimes when it goes to other body parts, like lymph nodes or other body parts, it will be a very, very small deposit. And it changes the prognosis, it changes the disease outcome. So this technology can help us both at the primary site, depending on the software you're using, and it can also work, say, in this case, in a lymph node. And you see the big pink cells with the nucleus in the middle, that's a tumor deposit coming from somewhere else. I can even guess where it's coming from based on my training, but it tells me that tumor is spread from the primary site to a secondary site just in this small area. And this technology is actually going to point us to make sure we look at it. So at this point, it's going to be a facilitator technology to make sure that the pathologist who's looking at it, this is why it's called augmented reality, because there is a real tissue on which it is being augmented with an image, essentially. So it's like a Snoopy dog or a smelling dog telling, go in this area, this is where the action is.
Yes, so I sure would want this kind of assistance in a diagnosis that I cared about. But you mentioned also, Nadeem, that sometimes you have to send these samples to another expert to look at. How might this approach address that problem?
Yeah, so what's going to happen down the line, this is, and I'm glad Katharyn understands, this is what we happen. Sometimes we will have difficult tumors, or sometimes me and my colleagues might disagree whether this is really tumor or not, or how bad the tumor is, and we will send this case out to, say, for example, someone in Washington, D.C., wherever we work. I work in Seattle, or might go to the university and all of that. As this technology is being trained and it gets better, I will have the access to those experts through the software growth, through this is AI growth, basically. So actually, and I've already used that. There was a case that I did in the, about last year, and this was me and one of my colleagues disagreed on the severity of the disease. We said, let's put it through this technology and see, and actually that technology supported me. And you could see the smile on his face, and this is arbitration, essentially. And this is why I'm so excited about this technology, that this is like bringing so many experts to your desktop while in the workflow, while in the flow of things. This is not something you have to learn. While, as long as you have the software, as you are running the slide, it will start giving you the heat map or the diagrams that Scott showed you, and then we'll show you probably, and make sure that we identify that. So this is brilliant where it's going.
Okay, so the problem of error-prone and time is made even more obvious through this discussion. So again, what did we do? How did we solve this problem?
Can we go to the next slide? I think, so we had the four of us, right? The three of us plus the arm on the intro slide. I think the arm must have missed its flight to Vegas because only three of us showed up. But this is what it is. It's a microscope. It's something that Dr. Zafar and his colleagues around the globe use every day to look at tissue specimens and try to find cancer. But it's different. You see wires coming out of it. It's instrumented with a mirror that splits the signal coming from the sample into two. One goes up to the eyepiece, where the pathologist, she's looking at it, and the other goes into a computer. It goes into this little machine. It's an edge device. It's not connected to the internet. It's not dependent on anything and Google infrastructure or government infrastructure or anything else. And it's running inference. Inference is the idea of running AI and making decisions, things like classification. And the result of that inference feeds back up into the microscope, and the output of that is, if there is something that the algorithm says, I think this is cancer, it will do an electronic highlight. So if we can go to the next slide, we'll see a sample of what this would look like to the pathologist. So here she's scanning around a sample, looking around, and the algorithm says, I think I see something, and there's a little yellow highlighter. So it's interesting. Dr. Zafar described the idea of arbitration, of suggesting. We've seen AI say, oh, this is an answer. But we've all seen AI miss badly, whether it's a story of a self-driving car that went off the road, or in your own life, in your own career, of something that's in one of your domains. But when AI taps you on the shoulder and says, hey, why don't you look over here? That's assistive, that's helpful, it's not making a decision. And that was an important lesson we actually learned in doing this work.
Yeah, so in this video, this is not being speeded up, just to let you know how real-time this is. The video is not being speeded up. This is exactly how we practice and all. The thing is about this microscope that's being shown to you. If you go to Africa, if you go to Asia, if you go to Europe, you will still see the same microscope being used. It just needs to be modified a little, not a whole lot. And that should be attached to a computer with the software in it, and then bang, you're ready to go with that, no matter where you are.
I mean, this notion of having the best expert available everywhere is very empowering.
Absolutely.
And so why now, Nadeem? Why is this technology now able to make a difference for pathology?
Actually, I would flip the question, why not now? Because everything I'm using, like, Scott talked about, self-driving cars, and, we use different platforms in a social life and all of that. They are now heavily supported by AI. Radiology, I've been talking to folks about radiology in this expo today, but there was nothing in pathology. And pathology is where the diagnosis for cancer comes. We are not preparing enough pathologists. The healthcare budget is going up. Actually, I can tell you in 2025, it'll be, just for healthcare, it'll be $5.6 trillion. And by 2030 it'll be 6.8. And this is much quicker or much bigger growth than the GDP, essentially. This is where the action is. And so this is the right time to begin to make sure, and the cost of errors is very high.
Right.
We want to make sure that we use this technology is brought into pathology, and we want to make sure that the diagnoses we render are very accurate, very timely, very efficient, and this is perfect.
I have a technical view on that too. AI has been around for a long time. It was, 50s, 56 I think is when it kind of became a thing. And there's been lots of cycles, hype cycles, mostly resulting in disillusionment. But the amount of data, the capability of the algorithms, the deep learning networks, those kinds of algorithms to do these kinds of things, and the availability and cost of compute, right? The GPUs, TPUs, that we've created at Google, to be able to bring high-scaled compute to various branches of AI have made this solvable. And so, you have a partnership with Google and the Department of Defense and actually a hardware company as well. Now we can solve it.
So Google had a role in the technology, but also in the orchestration. Scott, what was Google's role in this?
We did. So what's interesting about this is it was a very multifaceted problem. So looking at the entities that came together to solve this, you have Google, and we brought our subject matter experts, we brought our DevSecOps professionals, we brought some of our medical professionals that knew pathology and weren't pathologists, but knew that. Our cloud, all the stuff that, the capabilities of cloud, program management, just kind of all of that. But we didn't have the base of doctors, the medical treatment facilities. We didn't have all the data that we needed to create algorithms. We actually created 2, and then 2 more later, so we have 4 operational algorithms getting results now. And then hardware. Google's not an individual medical hardware company, so a company called Jenoptik came in and we partnered with them for the hardware. So it was really a coalition of these companies. To your question directly about Google, this was a really magical cross-functional effort. Like I said, there's all these different roles. There's even technicians, right? Thinking about vibration, power continuity, the network connection needed to scan 500,000 slides, which now these scans are 2.5 gig per slide, to be able to get that uploaded into the cloud and manage all that data and not take years and years to do it.
Amazing. Nadeem, what excites you about this?
I mean, this is kind of, so just to clarify my role, I'm an end user of this technology. So this was a collaborative partnership between Google and Department of Defense, essentially, and Jenoptik, the hardware company. So they approached us, and we have Department of Veterans Affairs, we deal with the veterans, basically. We are 144 hospitals, a big hospital system, one of the biggest in the world, essentially. So we provide a lot of diagnostic care for a lot of veterans, just like Department of Defense provides a lot of diagnostic care for the active servicemen and women, essentially. So we want to make sure, and now we have facilities where we have typically 1 pathologist, sometimes 2 pathologists, and they do their job, but they may not have all the expertise in the world, basically, and they may have to use support from other pathologists and all. I see a potential for this microscope and this technology, and the beauty is that pathology is moving in 2 different directions. The diagnostic, surgical pathology, cytopathology, whatever, they're moving towards digital pathology, which takes a lot of space and all of that. In this case, you don't even, the system is trained on images, but in this case, you don't need that storage space and all. What you are using is actually this technology in the usual flow of things. And that is so the change factor is brilliant in this one. And this is why I see much quicker adaptability, much quicker placement, and something which will not take us away from, if I have to go to work without a microscope at this point in time, I will be totally lost. Yeah. This is my bread and butter. This is what, this is who I train with and all. And so this technology just reinforces that, makes my job easier, makes my job quicker. And it actually opens up opportunity to train technicians, to more support people, to make sure that they have jobs and they can make our work even more efficient down the line. This is what this excitement is all about.
Yeah, it's really powerful for any of the use cases that you're considering is to involve the user, obviously, early in the process. But the change management, when this sort of, leader-led learning or this notion of the user expert being key to the project, we find the adoption just accelerates and the excitement accelerates. And we know from many studies, the more that we use AI, the more confident we are in it. And you've seen that as well, Nadeem,
right,
in your process. So the solution is the ARM, where it utilizes these AI algorithms to analyze these digitized tissue samples and highlight the potential abnormalities in real time. As you saw, or as you heard, this is not sped up, and it aids the pathologist in diagnosis. So we have the problem, the solution. So now, Nadeem, where do we go from here with this?
So, I mean, this is, like I said, this is the beginning of the story. And so far we have 4 algorithms that, Department of Defense and Google have worked with. One of them involves prostate cancer. One of them involves cervical disease, for example, dysplasia, HPV, very common all over the world, essentially. There's an algorithm for what you're looking at as nodal or lymph node metastases, and there's one more for mitotic count. This is only the beginning. And so, I mean, I think it's important for this collaboration to continue, this growth to continue. And there's growth, and this growth can bring both improved diagnosis, and I think there's a very good case for profitability for people who are involved with this model, essentially.
Is it essentially changes and scales and addresses, the problems we see across the system in a much
That's
more
correct, and actually the entire world is a market for something like this, because people come from other countries to train here, just like I did many years back to train in this country. Now what we are doing is we are bringing the trained teacher to them, assisting pathologists in different parts of the world, making their life easier, cutting down on their error rates as well, and making sure that the care quality improves, basically.
Amazing. Scott, from a Google perspective, where do we go from here with this solution?
Since we started this work 4 or 5 years ago, we've made a lot of investments in bringing healthcare-specific capabilities into our cloud platform, into GCP. The healthcare API is the main inroad to do that. So, as I mentioned, this is an edge device, which is fantastic because it doesn't rely on a network connection. It doesn't require connection to cloud. But it essentially introduces geographic asymmetry into the pathologist's mission. It says that this pathologist with this device at this location can solve the problem with an expert on her shoulder, and this pathologist in West Africa, who may not be DoD or may not have a microscope at a DoD facility, cannot. And so using that API and bringing this capability into cloud, batch, as we used to say, batch mode, solving this problem in batch so that we can take pathologists' needs from around the globe, regardless of their well-being. Is it a third world nation? Is it a first world economy? It doesn't matter because the cost of solving this is so low. And if there are 100 films per patient or 1,000 films per patient, bringing that into the cloud and doing it at scale and getting an answer back in a matter of seconds, because of how the cloud works, so bringing geographic symmetry. And I want to emphasize a great point, I think, that you made. There are a lot of different diseases, not just cancers, that can be solved with this data. And I actually threw a slide in, the next slide. It's like the Library of Congress, but these are physical tissue samples behind me that you're looking at. And so what if we took these, which number almost in the 100 million, and digitized them? And then took all the correlating information associated with each slide and built new algorithms, different types of cancers, different things associated with COVID that, apparently COVID existed long before COVID-19. The sky is the limit.
Yeah, if you think about this from a data standpoint and the extensibility of what we're talking about, and wherever we have massive amounts of data, where we require high skills, but perhaps there's a shortage of skills. And I say importantly, where there's variability and where time matters, we have a use case, or we have the potential for a public-private partnership to address these broad systemic problems. So if we can sort of take a step back and imagine a future where AI assists pathologists, yes, but insert your own role. I mean, assists us in ways of detecting, diagnosing, or in this case cancer, but insert whatever that time-sensitive outcome is that relates to your role or the markets that you serve with greater accuracy and speed, we have the ability to do this now. So if you think about that as sort of a call to action or as an opportunity for the people in the audience, Nadeem, what did you learn from this experience that you would give as advice to any of the audience who are thinking about approaching their own use case?
So I think it will be very interesting for us to hear from them during the question and answer session, what brought them to this session. That'll be something very interesting so we can be more specific in our answers. But at this point in time, you need to understand that radiology or the X-rays or CTs are ahead of us because they have been digitizing images for a long time.
Right.
And pathologists are the new players in the field, or pathology is the new player in the field. So we have now been doing digital pathology for a while. So that's been done now, and as Scott indicated, there are glass slides in these containers that you can see. There are, hundreds of thousands of millions of slides in there. And I think it's time to start digitizing those and build up those AI-based repositories within the system. And it doesn't just have to happen in the US, it can happen in Europe, it can happen all over the world as long as they have the whereabouts or they know how to do it. And I think that's where the growth will be. And the point is that we want to make sure that the care we provide in future is much more efficient, cost-effective, quicker, accurate, and to make sure that, and the errors, when you introduce errors, it increases heartache and it makes the cost of care much more expensive. Because now you have to rectify errors. This technology will, while we are doing what we do as experts in our fields, will make us be even more accurate. It will help us train our residents. It will help us teach medical students and all of that, and then collaborate across the world if we need to, essentially.
Yeah, I know that the training aspect of this is so powerful. Scott, if someone in the audience would have a similar kind of use case, how might they engage with Google or with any of the kind of ecosystem partners?
I'll bet they do. I mean, what we're looking at here is a giant pile of data, a problem that needs solving, and a bunch of committed people with a partnership, across a couple different organizations to solve it. That I would be surprised if anybody in here said, "Oh, I don't have a lot of data or a problem like that or something like that." I mean, whether you're government, whether you're industry, this may be something that is reflective of your organization. So I love Google. We have a lot of wicked smart people. I get to work with some great people, but we know that we can't solve these kinds of problems alone. So the partnership that we have with the government has been fantastic. Bringing the subject matter expertise, bringing the data, bringing the commitment to solving this problem with us helps us to do the mission that we have at Google, making information available and accessible, curing cancer, making the human condition better every day.
So if I can just add to that, for the audience to understand, there are two particular, in this case, Scott talked of the government. In the Department of Defense, there's something called Defense Innovation Unit. That's the one which were the main partners that were movers and shakers in this. And this is, by the way, came from your funds. This is taxpayer money. And then we, in VA, it's called Office of Health Innovation and Learning. And I think if people are interested, then we can talk about it and we can connect you with the people out there to keep this process moving if they're interested with that.
Yeah, the workshopping aspect of this with the expertise across the system is really powerful in terms of where we are and the ability to solve these problems. So with that, join me in thanking the panelists and let's go change the world together. Thank you, guys.